first of all, I would like to thank to the organizer for giving me this opportunity. Okay, I am so. This is my abstract, as you have already. So I'll be talking about something on the recent discovery of time delay in photoannihilation, and thereafter some more experiments and the theoretical studies which has been actuated from that experiment, and also some of our known contribution to that to this field. So first of all, uh, uh, what is time? Time plays an important role in quantum theory, but absolute time has no meaning. Only passage time has meaning, and what we can measure. And the recent development, let me not read all these things. Recent developments in ultrafast laser technology has revealed that this short time scale of attosecond regime is measurable, and you can see the atomic and molecular motions in their own time scale, which is of the order of attosecond. So I will be talking about what is time delay. So let us first consider, let us first spend some time what is the meaning of time delay in real life. Well, let's say that I'm going to my office and I met some friend. So I will be talking for some time and I'll be late. So that means that I will be late in my office. So it gives a delay in my reaching time. Well, it can be advanced. Yeah, it can be. Because if I'm chased by a dog, I'll be advanced in time. So this is real, and in quantum mechanics, if we solve the Schrodinger equation, I'll be able to. Sorry, it is not running. Anyway, so if I start with a wave packet, I'm not able to show the wave packet. If I start from here, then if I keep a potential well from 0.6 to 0.8, it will reach here. Some part of the wave packet will be reaching here, and some part will be reflected. And we can see that free evolution, which is the red line, and the reflected and refracted part, which is actually having this scattering part, is the blue line. They are having some difference in between their peak. So that actually basically represents the time delay in quantum settings. Okay. So what are the time scales in our day-to-day life? We are living in seconds time scale, where our heartbeat is of the order of second. Or this fastest camera like 10 to the power like microsecond regime, and or electrical microchips response like 10 to the minus 9 nanosecond, and molecular vibrations takes place in femtosecond, and if we go to the electron in atom, it will be attosecond regime. Okay, so attosecond is a very tiny time. It is as small with respect to a second as 1 second is small with respect to the age of the universe. We know the age of the universe is 10 to the 73. So I will be talking about photoionization. So what is photoionization? It is the ejection of electron if we shine one atom by some photon. Okay. So earlier contention was that the photoionization is an instantaneous process, and after the discovery of from Schulz group, Franz Schulz group, that it is not an instantaneous process. It is there is a time delay associated with the photoionization. So what is the importance? The importance is to set the zero of time on atomic clock time scale, and it will provide a probe for modeling mini electron dynamics. Okay, so depending on the initial state and the evolution process, the time will taken by the particle will be different. So what Schulz have found in 2010 is that the 2s and 2p electrons will take about 20 attosecond time to reach the detector relative to each other. So with that, I am going to stress that what did they measure? They have actually measured this whole quantity, where the streaking time delay can be divided into these parts. But basically, this is the atomic potential part, which is the Heisenberg-Wigner time delay, and this is the measurement-induced part. So I will be talking about this Eisenberg, focusing on the Eisenberg-Wigner time delay. So what is that? According to Eisenberg, Wigner and Smith, uh, the the phase shift accumulated by a scattering particle is connected. It can be connected with the time delay. If we take the energy derivative of the phase shift, it will give the time delay. The relation is this one. So how to measure this short time scale? So we can measure in terms of in this experimental technique called attosecond streaking. So I'll just briefly describe what is a streaking technique. If we send a light pulse, and if we keep a keep some screen, which will some photoelectrons will be ejected from this light pulse, then these photoelectrons can be accelerated perpendicular direction in this perpendicular direction with the application of some high voltage time varying electric field. Then these photoelectrons will come here, and it will the time domain of this incident light pulse will be mapped into the spatial domain of this fluorescent screen in this fluorescent screen. So we can see what is the temporal structure of this photon in terms of this spatial distribution of this fluorescence. So this technique actually have used for this capturing the this electron motion in atomic time scale. So what did they do? They have sent some XUV photon in the atom, and with that there is a delayed IR radiation which has also has been sent, and okay, whenever an atom is ionized, depending on the phase of this IR photon, it will get some extra kick, extra momentum. So you can get a momentum distribution depending on this equation in the final state electron, and depending on the delays, you can get what is the time delay in emission process. Okay, so after the discovery of 2010 switch 20 attosecond of time delay in 2s and 2p orbitals of neon atom, there are some more experiments. I have mentioned here the Flunder's experiment, and there are some theoretical studies. So in theoretical study, what they are doing, they are basically calculating the matrix element. So matrix element between the initial state and the final state, and if we write down the matrix element in dipole operator form, then this term is related to the cross section, and this term, this phase shift, will be related to the time delay if we take the energy derivative of the phase shift in terms of the Wigner formula. So what is our motivation? As we can see in the literature, that most of the studies are non-relativistic, but they are many-body theory. And we can study in relativistic formalism. And relativistic many-body theory is important because single electron even if one single electron will be ionized in the ionization process, it is not a single particle process, it's a many-body process. So we have to include proper many-body theory to describe the atomic photoionization. So we have incorporated this many-body theory, which is called the random phase approximation in relativistic form. These are some of the differences. And well, we have calculated the time delay in these regions, and we can see that it matches not very much accurate, but matches within the experimental ranges. And we have extended our calculation in this super minimum region, which is an important region in this energy spectrum. Well, next work we have done some confinement oscillation studies on time delay. So as you all know that atoms in various confined systems, they are not free. They will be applied with some extra potentials. So in Fullerene cage, if we keep an atom, then it can be modeled with an attractive spherical square well potential, and then we can solve the this potential in this approximation, and this is our result. I'm not showing any equation or anything, just showing some results. So if we see the free atom case, then there is no oscillation as you can see, but the cross section will be having oscillation if we calculate in this encaged atom, and there will be oscillation present in this time delay domain also. And we can see if we compare these two, we can see that the prominence of the oscillation is much more in this time delay domain. So we propose that these confinement effects can be studied in time delay domain rather than in this cross section and all these other parameters like beta parameter and all these things. Much more better way. One more thing I'll just shortly discuss. So as you all know that this photoionization process is anisotropic. Why? Because whenever an atom is given some laser or photon, then with respect to the polarization direction, the ejection of this electron is not isotropic, it will be anisotropic. So what will be the anisotropy in the time delay? So we can calculate the anisotropy in the time delay. If we see the matrix element, then we can see that it will be involved these Y elements, okay. So basically depending on the final states, so let us consider that from P, initial state is P, then in dipole approximation P to S and P to D are possible, two states. Then the final state will be having different Y elements. So they will interfere with each other and it will create an angular dependence in the time delay. So we have calculated some of these angular dependence of the time delay, and you can find a detailed discussion of these things in this paper. So with this I would like to conclude that this is important in the quantum theory because the basic understanding of atomic and molecular processes involves the like how can you describe any observable with our understanding of quantum theory of atoms and molecules. So if we can understand atoms and molecules better way, then this description will be better. And also it can be better probe. It can be a better probe to nanostructures. So with this, I would like to acknowledge my supervisor and collaborators and some of my colleagues. And thank you all for your kind attention.
Any question from the audience?
You were saying you're looking for the zero of time in your experiments. Is that what you meant with one of your graphs had actually a negative delay?
Can you?
Okay.
Okay.
One of your graphs had a negative delay time.
Negative.
Is that what the experiment?
Yeah, it is also possible because as you have mentioned that the electron can get some advance in kick. Okay. See, if it is depending on just the potential and the energy of the photoelectron, okay, you can see the initial state of this electron and the final state. So if we take if we calculate the phase shift, then it may have some advance in time also. So all the time it may not have the delay. It can be advance also.
Okay, thank you.
So if there are no more questions, let's thank the speaker again.